Welcome back to this series of video. Today's video is about the conditions of equilibrium in 2D configurations. Today I will be talking about the conditions of equilibrium, like I said, in 2D configurations, and I will give example of calculations after. The condition of equilibrium in 2D, and it is also valid in 3D, but today's is only about 2D, is the following. Sigma of the forces equals 0. The forces are the exterior forces, and sigma of the moment about an axis or center of rotation, I will say O, for example, equals 0. These are the two conditions of equilibrium, and they are sufficient to calculate, to solve the problems. So when you have a system in equilibrium, the resultant, which is sigma of the forces, the resultant of all the exterior forces acting on this system is equals to 0, and all the moments acting on the system is equals to 0. If it's not equals to 0, that means the system is moving and we move to the dynamic situation. These two conditions are necessarily and sufficient for solving the problems. Here I've got on the board an example on which we have a beam on which two forces are applied on this beam. Now, what we want to do, the question is to find the reactions at the supports for the beam. That means the reaction at A and reaction in B. So how can we solve this problem? It's by using these two conditions. Sigma of the forces and sigma of the moment equals 0. So before starting the problem, solving the problem, we have to set up a system of axes. I will say, for example, X and Y, and we have to choose an orientation of the moment. I will consider that the moment turning clockwise, this moment is positive. So clockwise is positive. To the left, X to the right, is positive, and up is positive. I will start by calculating the moment, for example, on A, but before doing that, I have to draw the forces acting on A and B. Here we have a hinge, a pin, and here we have a roller. So when we have a pin and roller, the pin will oppose this movement. So it will be R A, but according to Y, and another component here, R A along X, because we have a hinge, a pin. For the roller will only oppose the vertical movement, and I will name it R B along Y. There is no component along X. So here R I X and I. AY. So what I will do, I will start by writing sigma of the moment equals 0. Sigma of the moment equals 0. But where I have to choose my moment, the best point to choose the moment here is A. Why? Because when I pick A, I will eliminate the moments of RA and RAY and RAX, because they will have no distance from the point A. So I will write sigma of the moment at A equals 0. So what we have as the forces, we have now this one, and this one. Of course, this 30 newtons kilonewtons has two components, one along X and one along Y. Along Y and along X. So now I start my calculation. Sigma of the moment along around A is, we start by this, the first force here. So the moment of RAY is 0, the moment of RAX is 0, because the moment, as we have seen before, is force times distance. The distance from the distance from the point of application to A is 0, because they are applied in A. Now, sigma of the forces, I will start with by this one, turning clockwise. I have sigma now, the moment about A of the total moment, 50 newtons times this distance, 50 times 10. I recall that moment is force times distance. After that, I have this force, and this force, the vertical component of this force along Y is, I have here 45 degrees is 30 sine 45, 30 sine 45, and the distance from this point to this point is 20. So plus 20 times 30 times the vertical component, which is 30 kilonewtons sine 45. And this force is acting down, that means is turning clockwise. Now I move now to B, and to B I have this distance from A is 30 meters. 30 times what? Times R, the reaction at B along Y. In fact, I've got only one component, because we have a roller. I can just take RB and get rid of this Y, just RB, because we don't have a horizontal component. Now this RB is pushing up, that means is anti-clockwise. I have to put minus. This is the first condition. This first condition will give me this equals to 0. Therefore, I've got RB equals 50 times 10, which is 500, plus 20 times 30, 600, sine 45, divided by 30. I did the calculations, and you got RB equals 30.8 kilonewtons. So now I can come here and put and write RB equals 30.8 kilonewtons. This is by using the first condition, sigma of the moment equals A. Now, I will rub out this. What I'm going to do now is to use the second condition, which is sigma of the forces, the result, all the exterior forces equals 0. I'll start by writing sigma this, because this is in fact is a vectorial relation. I'll have to project this relation along x and y. I'll do it along x, along y. So along y, what are the forces? Along y, I have RAY minus 50, because it's going down, minus 50 kilonewtons. This one, 30, has a component which is 30 sine 40. RY equals 50 plus 30 sine 45 minus 30.8. This will give me the reaction, the vertical reaction in A, and this is 40.40 kilonewtons. Now I've got this reaction. Now I'll determine this one, 40.40 kilonewtons. The same thing now I need, because I need now to find the horizontal component of R in A, I'll have to do along, I project this relation along X. So along X, what I have RIX, RAX going to the right direction, and this 30 newtons is going to the left, so I have to put minus 30, and this time cosine 45. Of course, this should be equal to 0, and but now LA along X equals 30 cos 45, and I get this answer, which is 21 kilonewtons, that I put here, 21 kilonewtons. Now I'm nearly there. I have just to give now the direction of the resultant at A, because this resultant in A at A has two components. Finally, the reaction is something like this at the point. So this reaction has this direction that I should determine. I've got the component along Y and the component along X. So now it becomes easy. I have just to use Pythagoras theorem, and R squared equals RAY squared plus RAX squared. R in A, of course, squared equals 40 squared plus 21 squared. This will give me RA equals to 4563 kilonewtons. And as you can see, by using these two conditions, sigma of the forces and sigma the moment, I am able to determine completely the reactions at A and B. What is needed now is just to give the direction of this reaction by writing that tan theta, if I choose here theta as this angle, tan equals opposite upon hypotenuse is 40 times dot 40 kilonewtons divided by 21, which gives me theta equals to 62.3. 62 degrees point 3. So we have seen on this example how to find the reactions at the support when reactions are applied at different places by using sigma of the forces equals 0 and sigma of the moment equals 0, means the sigma of the exterior forces applied to the body. Thank you very much for your attention and see you in the next video.